Hello, calculus fans. All right, let's talk about the series where we're going to sum from n equals 1 to infinity of 1 over n squared. And what we're going to do is draw a graph of y equals 1 over x squared along with some rectangles that will help us see the series. All right, so here's our graph of y equals 1 over x squared. And then we're fitting in some rectangles so that the heights of the rectangles are the terms of the series. Sure, you should see things like this rectangle here has height 1 over 2 squared because we're using the right endpoint, which is 2, to plug into the function y equals 1 over x squared. Every one of these rectangles has base 1. So altogether, the areas of these rectangles, well, we have 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared and so on. That's the sum of the areas of the rectangles. 1 over 1 squared plus 1 over 2 squared and so on up to 1 over n squared. And we just keep going forever. And so we get this series. The sum, n goes from 1 to infinity, of 1 over n squared. Now let's throw away the first rectangle. The total area of the remaining rectangles is smaller than the area under y equals 1 over x squared for x bigger than or equal to 1. Basically, go back to that picture and ignore the first rectangle. Now let's calculate the area under the curve. That's the integral from 1 to infinity of 1 over x squared dx, which we'll write as a limit. That gives us a fairly easy antiderivative. So we wind up with the limit as m goes to infinity of negative 1 over m plus 1, and that equals 1. So that's the area under the curve. So our series, now remember, we ignored the first term of the series because we're ignoring the first rectangle. What's left over, the remaining rectangles going from 2 out to infinity, is smaller than the value of the integral. So altogether, the sum of the series is no bigger than 2. So what this really means is that the partial sums are bounded above by 2, and that implies that the series converges. And it also tells us that the sum of the series, whatever it is smaller than 2. It's not equal to 2, but it's definitely smaller than 2. Euler proved that the value of this series is actually pi squared over 6, and that's a little less than 2. It turns out this is a bit beyond what we're really going to be able to do in this class. Okay, let's try another series. So now we're going to sum n goes from 1 to infinity of 1 over square root of n. Now this series, turns out it diverges. You could actually guess that if you looked at partial sums and you went out far enough. Now to prove this, again, we're going to look at a picture, but this picture will be slightly different. So it's the same kind of picture where we draw rectangles according to a curve, but this time we choose the height of the rectangle on the left end. And now our rectangles are going above the curve. So the sum of the areas of the rectangles is the series, n goes from 1 to infinity of 1 over square root of n. Remember, each rectangle has width 1, so we're really only concerned about the heights. This total area is larger than the area under the curve y equals 1 over square root of x for x bigger than or equal to 1. All right, let's calculate that area. That's an improper integral. Integrate from 1 to infinity of 1 over square root of x dx. We'll write that as a limit, compute an antiderivative, and plug in the m. If we take a limit, we end up with infinity. So that area diverges. That tells us that the series is divergent because the series is actually larger than the area under the curve, which turned out to be infinite. Now this reasoning that we've gone through with one convergent series and one divergent series can be used to prove this theorem. This is the integral test. So let's suppose that you have a positive, continuous, decreasing function which is defined on the interval from 1 to infinity, and that function gives you the values of your terms of your series for all n bigger than or equal to 1. What the integral test tells you is that the series converges if and only if the corresponding improper integral converges. So if one converges, the other converges. If one diverges, the other diverges. And the way we'll use this is that we've already got some practice with computing improper integrals, so knowing about whether or not the improper integral converges will tell us something about the series. Couple of notes: it's not necessary to start the series or the integral at 1. You can start them anywhere, it doesn't really matter, so whatever's convenient. It's also not necessary for f to be always decreasing, just eventually decreasing. That is, it has to be decreasing starting at some point n and beyond. We don't really care what happens at the beginning, we care about what happens to the tail of the function. Okay, that's all for now.